Good morning, everyone. We're going to perform an experiment with this relay right here and show the importance of the spike suppression diode across the coil of a relay. The spike suppression diode is also known as the catch diode or freewheeling diode. This experiment involves this 120 volt AC neon bulb in parallel with the relay coil. I'm going to energize this relay and then quickly remove the current from the relay coil, and we'll watch this light bulb light up just briefly. But remember, we're putting 24 volts in, but we're getting enough energy back out of that coil to light up this 120 volt AC light bulb. Now we'll also look at the waveform on the oscilloscope. But let's energize that relay. The relay just closed. Now I'm going to release the relay coil from the power supply. Turn the lights off and put the camera closer to that neon and you'll see it light up. Alright, let's energize the relay. I'm going to turn the relay off. On, off, on, off, on, off. Isn't that amazing? That's amazing that you can apply 24 volts DC to the relay, remove the coil from the power supply, and light up that neon bulb. That is amazing. Okay, let's look at the waveforms on the oscilloscope when we turn that relay on and off. Now we're going to look at the waveform generated when we release that relay coil from the power supply. I've got the meter set to hold mode so that the waveform will stay up on the LCD. Look at that. We have a peak of almost 200 volts on the positive side and a peak of almost 400 volts on the negative side. If we were turning on that relay with a switch, that switch would not last very long. The lifetime of that switch would be greatly diminished. And if we were turning on this relay with a transistor, that transistor would be damaged if the collector emitter was not rated for these types of voltages. So to prevent damage to the devices that turn on this relay coil, we add a diode, and it's called the freewheeling diode. I'm going to install the freewheeling diode and we'll see what happens. Here's the diode that I'm going to use. This is a 1N4007. You want the cathode to go to the positive side of the voltage that's turning on that relay, and you want the anode to go to the ground side. So let's see if I can get this in here without losing my wires. Really ought to put my close-up glasses on. There's one side. Cathode to the positive. Oh, lost my neon. I wanted to show you that the neon would not be turning on with this diode in here, so let's try to get that neon put back in there. I'm going to put my close-up glasses on. That's better. Get in there. Don't get squirrely. Okay, there's the other side of the neon. Alright, let's watch that the neon does not turn on now. I'll turn this light off and I'll move the camera closer. Okay, the relay is on, off, on, off, on, off. And notice that the neon did not turn on. That is amazing. I'm going to take the scope out of hold mode because with the freewheeling diode in there, there's no spike. And in hold mode, it don't capture it. So let's see what it looks like if we get out of hold mode. Let's go down here to the menu, scope options, trigger, go to free run. We were on trigger, now we're going to free run. Let's see what we see. There, the relay is on. Relay off. On. Off. And with that freewheeling diode in there, we did not see the huge voltage spike. So if you want to protect the devices that turn on that relay coil, make sure that you put that freewheeling diode in there. And this works for DC voltages that turn on this coil. You have to use an RC network if you're turning an AC coil on. An RC network is also known as a snubber. Alright folks, hope you enjoyed that experiment right there that demonstrated why we need to use the spike suppression diode. Evening all. It's been a couple of days since we performed this experiment with the freewheeling diode. Here is the circuit. And at this moment in time, I have closed this switch. And current is flowing through the coil, creating a magnetic field. That magnetic field builds up and current is flowing in this direction, and we have positive from the power supply on this end of the inductor and ground negative on this side of the inductor from the power supply with that switch closed. Let me move this out of the way and we'll see what happens when we open this switch. I've opened up the switch, and now notice the polarity. The collapsing magnetic field cuts across the windings in that relay coil, and now the polarity is reversed from what was creating that magnetic field, and current is flowing in the opposite direction. The magnetic field collapsing upon the windings of that coil induces a large voltage spike, and that's what fires this neon to turn on, is that magnetic field collapsing across the coils of that inductor or that relay coil, and it generates that high voltage spike, enough to turn on that 120 volt AC neon light bulb. Now what I'm going to do, notice the polarity. The current flow is in this direction. The polarity has switched. Now down here it's positive and up here it's negative. I'm going to draw the freewheeling diode into this circuit. Let me see if I can do that. I'm reaching around the camera. This is the polarity of the freewheeling diode. Now look at this. Remember when after we had installed that freewheeling diode, the neon did not light up? look at this. With the switch opened, we have positive down here and negative up here. And look at this, we have forward biased that diode. We forward biased that diode, and now all of that high voltage energy is maintained within this circuit right here. The forward biased voltage, the ground up here, anode here, cathode there, forward biased diode, and all of that energy, until that magnetic field is fully collapsed, is retained within this circuit right here. And that's why the neon didn't fire. That is so cool. That is amazing. The people that thought of this type of fix were geniuses. Just putting that simple diode in there prevented that high voltage spike from damaging this switch right here. Or let me put up another circuit in a minute. I'll show you how we turn these relays on with transistors, and how without that freewheeling diode, that transistor, that NPN transistor, would be destroyed. I'll be back in a little bit. I got to make another drawing. Here's a typical NPN transistor circuit used to turn on a relay coil. Now here's a relay coil right here, plus 24 volts DC from a power supply, and ground down here. This is a 24 volt DC relay coil. Here's the switch used to apply the DC voltage to the base emitter junction of that NPN transistor. It's current limiting resistor right here, and this resistor down here ensures that when the switch is open, the base is connected to ground so that it's turned off. Let's close the switch. We apply a base emitter voltage that turns on this NPN transistor, drives it into saturation. Current flows from plus 24 through the relay coil, through the transistor, back to ground. So our current flow is in this direction. We have a positive up here from the plus 24, and we have a negative here to ground. Let's open up the switch. Now we've turned off the transistor. The transistor collector emitter junction is no longer conducting. When it was on and turned on, the magnetic field expanded to its maximum. Now that it's off, that magnetic field collapses across the windings of the coil of that relay, inducing a large spike. We saw it in the oscilloscope waveforms how large that voltage is, much greater than 24 volts DC in our experiment. And look at this. We have an NPN transistor attached to that coil. The polarity now being, let me write that in over here, the polarity now being positive down here and negative up here. Ignore these two polarity markings right here of when the switch was closed. Now with that large spike, it's going to destroy this transistor. These transistors are not meant to handle those huge voltages. Let's say we had a transistor with a collector emitter max amplitude between the collector and emitter of 100 volts. Well, that's a good voltage for this 24. That's plenty of voltage rating from collector emitter for 24 volts, but it isn't for 800. So let me erase these guys out of here. They're no longer in play because now we've opened up that switch and the magnetic field is collapsing. Notice the polarity is plus and minus. Now let's draw in the freewheeling diode. I'm reaching across the camera so my drawing might not be that great. Here we have just added our freewheeling diode. Notice that with the magnetic field collapsing, the polarity is reversed from the external power supply when we first built up that magnetic field. The magnetic field is collapsing. This is positive. Here's our anode. This is negative. Here's our cathode. We have just forward biased that diode right there, and all of that energy stays within this loop right here until the magnetic field is fully dissipated, protecting that transistor right there, and also protecting our little 24 volt DC power supply out there. Don't forget about that. That is the purpose of that freewheeling diode, that spike suppression diode. It prevents that high voltage energy from damaging external components. Nice. Nice. So now, when you look at this diode here across the relay coil, you'll know why it's there. That's cool, isn't it? Okay. Alright, folks. Hope you enjoyed that experiment with the spike suppression diode, the freewheeling diode. Have a good night. It's getting dark around here. We'll see you next time.